I hope everyone is safe at home. Today's session I am going to teach the preparations and the chemical properties of phenols. Phenols are again hydroxyl compounds, and here to aryl group OH group is connected. You know about phenols. The structure of phenol is here written on the board. This is C6H5OH. Now today I am going to explain the 4 important preparation techniques of phenols. Coming to the phenols here, let us go with the flowchart method. As I tell you that this is the best method to remember any type of chemical reaction of any organic compound. So there are 4 methods. The first method, we go with chlorobenzene. So we can prepare phenol with chlorobenzene. And the second method you have here, the first method with chlorobenzene. And coming to the second method is benzene sulfonic acid. We can prepare phenol from benzene sulfonic acid. The third method comes here is with diazonium salts. So you know about diazonium salts. In the last session we went with Sand-Meyers reaction where aniline, or let me say that aminobenzene, is converted to diazonium salt. These diazonium salts are also, these can also be converted into phenols. And the last but very important method is with cumene. What is this cumene? Cumene is isopropyl benzene. So let us start stepwise. The first one is chlorobenzene. This chlorobenzene here, you can you know about the formula of chlorobenzene, C6H5Cl. This C6H5Cl chlorobenzene is treated with aqueous NaOH. Here, this is an substitution reaction, aqueous NaOH. But you know that this is a nucleophilic substitution reaction. But this nucleophilic substitution reaction is very difficult in aryl halides. So here, certain temperature, 623 Kelvin and 300 atmosphere. This is the let me say the parameters where this reaction can be comfortably done. So chlorobenzene is treated with aqueous NaOH at 623 Kelvin and 300 atmospheres. First of all, this chlorobenzene is converted into sodium phenoxide here like this. This is C6H5ONA. This is called sodium phenoxide. And then later this is again acidified. So this H plus is nothing but when it is treated with any type of dilute acids release H plus. We call this particular reaction as acidification. Then you can understand that this Na plus can be substituted by H plus. So you will be getting the byproduct as phenol. This is phenol. So this is the first preparation technique, how chlorobenzene is converted into phenol. Phenol is obtained from chlorobenzene by nucleophilic substitution reaction. Then we move on to the next one, benzene sulfonic acid. How do we get this benzene sulfonic acid? First of all, benzene undergoes electrophilic substitution with here like oleum mixture. So I am taking benzene. You know about benzene. Benzene is C6H6. This benzene is treated with oleum mixture, H2SO4 plus ESO3. This is called oleum mixture. When it is treated with oleum mixture, SO3H, that is an electrophile that comes in contact, and you will be obtained with benzene sulfonic acid. This is the formula of benzene sulfonic acid. Now, this is treated with here NaOH. 2 moles of NaOH is taken. Now here you can see there is an SO3 ion. This SO3 ion comes out in the form of sodium sulfite. Like here I am writing minus Na2SO3. This you have to understand. To make you understand, I am telling you that this SO3 is removed in the form of sodium sulfite. And there are 2 OH groups, and one of the OH group takes this and minus H2O. These are the eliminated let me say compounds, and then it results with here like this OH, phenol. So we can make or we can synthesize phenol with the help of benzene sulfonic acid. Now coming to the third one, that is diazonium salts. Here the important raw material which we take is aminobenzene. Aminobenzene is also called as aniline. Now I'm taking aniline. Aniline is C6H5 and H2. This aniline is treated with nitrous acid, NaNO2 and HCl. Benzene diazonium salt is obtained, and that benzene diazonium salt is C6H5N2Cl. This benzene diazonium salt is just now warmed with water. So here it is warmed with water. The nitrogen gas which is present here is coming out on here OH and here plus N2, and there is a Cl. The Cl comes in contact with the H plus from water and comes out in the form of HCl. So this is the third technique where aniline is treated with nitrous acid. It is converted to benzene diazonium salt, and this benzene diazonium salt is used in synthesizing phenol. And the last technique is cumene. That is, cumene is isopropyl benzene. What is this isopropyl benzene? Here, this is isopropyl. Iso in the sense the second carbon is always the active carbon. So here CH, CH3 and CH3. This is called cumene. This is the structure of the molecule cumene. We also call it as isopropyl benzene. This is oxidized in air. In air, majorly oxygen gas, it is undergoing oxidation. So two atoms of oxygen are introduced here. In such a way, intermediately you can see the molecule in this way, COOH, and here CH3 and here also CH3. This is an intermediate adduct that is formed, and simply it is hydrolyzed. When it is hydrolyzed or acidified, then you are getting two important compounds besides phenol. An important compound, namely acetone, is also synthesized here as an important byproduct. So what is acetone? Here you can see the molecule is broken like this, and this part I am writing as CH3 C double bond O CH3, and the remaining part is phenol C6H5OH. So in this way, here in the last case, both the compounds are like synthesized, and acetone, this is one of the preparation of acetone also. So these are, once again, I recapitulate everything. So here these are the four important methods of phenol. Usually this question is asked in the board part. And chlorobenzene, that is electrophilic substitution, nucleophilic substitution reaction is done here. Then benzene sulfonic acid is converted into phenol. Then diazonium salts are also, when they are warmed, they result of the yield phenols. And the important method of manufacturing phenol is with cumene. That is, cumene, when it is oxidized, here you will be getting cumene hydroperoxide, and then when it is acidified, it results in acetone as well as phenol. So I hope everyone understood the preparations of phenols, and this is the best method to remember the whole preparations in a flowchart method. Right? Okay. So the next one is the chemical properties of phenols. So now I'll be teaching you the properties, chemical properties of phenols. Chemical properties of phenol. Here there are majorly, again I'll be explaining you in flowchart method, electrophilic substitutions of phenols, and then you have named reactions like Cobb's reaction, Raymer-Tillman reaction, and then you have reduction of phenol and oxidation of phenol. As you know, electrophilic substitutions, here I am going to explain you nitration and bromination. How this nitration is done in phenol and how bromination is done in phenol. So the very first one is electrophilic substitution of coming here. The very first reaction in electrophilic substitution is nitration. So you know about nitration. Nitration, here you will be taking the reagent as nitric acid. Now dilute nitric acid and concentrated nitric acid, these two reagents give two different types of compounds. If you want a mono substituted nitrophenols, you will be using dilute nitric acid. And this concentrated nitric acid, it activates, or let me say the whole phenol molecule at ortho and para position, and a trinitrophenol is also obtained when concentrated nitric acid is used. So if you want a monosubstituted nitrophenol, you will be using dilute nitric acid. So there are two types of nitrations. So here you can look here. This is phenol C6H5OH. This, when it is treated with dilute nitric acid, dilute HNO3, then only either ortho, and like you can get both ortho substituted nitrophenol and para substituted nitrophenol. You know about the ortho position and para position. Ortho positions 1 and 2 or 1 and 6, and para position 1 and 4. So you will be getting two monosubstituted nitrophenols here. This is ortho substituted nitrophenol. You can write O nitrophenol. And along with that, you will be also getting another monosubstituted nitrophenol, like that is a para substituted nitrophenol. So in this way, if nitration is done in the presence of dilute nitric acid, you are obtained with two monosubstituted nitrophenols. And also one thing you have to remember, among these two, this is less volatile. Less volatile in the sense it has high boiling point. Why? You may be asking me why. So here, in both the cases, you'll be seeing a phenomenon called hydrogen bonding. But in this case, you'll be seeing interhydrogen bonding. And in this case, you'll be seeing intrahydrogen bonding. Because of this specific reason, here para-nitrophenols, they have high boiling points and they are less volatile. Now, the second type of nitration here you go with is with concentrated sulfuric acid. When concentrated sulfuric acid is taken as a reagent here, now the whole molecule is activated highly at all the three positions, two ortho positions and para position, such that you will be getting a tri-substituted phenol. So here one nitro group is connected, here another nitro group is connected, and here also another nitro group is connected. If you go with IUPAC nomenclature, you can say this as 2, 4, 6 trinitrophenol. This is also called as picric acid. So here the name itself is explaining that the acidity of phenol is very much increased due to three nitro groups that are introduced when the same electrophilic nitration is done with concentrated nitric acid. This is the nitration. Then the second one is bromination. You know about bromination. Bromination in the sense, again, bromonium electrophile is introduced into that phenol. Here also in this case, usually electrophilic bromination is done in the presence of that Lewis acid, Friedencraft's catalyst, namely ferric bromide. Now, here also there are two types of reactions. Now the phenol here, this is undergoing this bromination with the bromine in the presence of no need to take that ferric bromide, in the presence of organic low polarity with the solvents which have low polarity like chloroform and carbon disulfide, CHCl3 or CS2. Either of these organic solvents can continue the electrophilic substitution, such that you will be getting monosubstituted bromine. Here you can say this is orthobromophenol, and then you will be getting para-bromophenol, like this is OH, and here I will be writing bromine. These are the monosubstituted bromophenols. Now, if the same thing is done in the presence of bromine water, like here I am taking OH and bromine water, that is aqueous. When bromine water is taken as a reagent, here this is activating, the bromine water is activating the whole phenol molecule at all the three positions, and now you will be getting a tri-substituted bromophenol. just like above case, here also you will be getting the 2,4,6 tribromophenol, and this is, here I am writing the IUPAC name, 2,4,6 tribromophenol, and this is a white color precipitate. This is a white color precipitate. In this way, electrophilic substitution reactions in phenols are different with different reagents. If you want a mono-substituted phenols, you will be using dilute nitric acid in the case of nitration, and bromine, which is dissolved in CS2 or CHCl3. That is, these are the organic solvents which are having low polarity. So here water is taken, which is a wonderful polar molecule where it is activating the whole molecule to give tribromophenol. Okay. The important chemical properties of phenol include Scopes reaction, Raymer-Thaman reaction, reduction of phenol, and oxidation of phenol, besides the electrophilic substitution reactions of phenol. Now we start with the Scopes reaction. Scopes reaction is an electrophilic substitution reaction again, but here a weak electrophile carbon dioxide is taken. So because we are taking a weak electrophile carbon dioxide, first of all, phenol is converted into sodium phenoxide with the help of aqueous NaOH. Then it is converted into salicylic acid. Salicylic acid is hydroxybenzoic acid. Now, what is Scopes reaction here? I am taking phenol molecule. This phenol is first of all treated with aqueous NaOH. When we are treating with aqueous NaOH, we will be getting sodium phenoxide. Sodium phenoxide is C6H5ONa. This is the important step why we are converting phenol into sodium phenoxide, because here the reagent which we are using is a weak electrophile. This is weak electrophile. And this is done in the presence of mineral acid. Then you can get hydroxybenzoic acid. Here remove this Na and OH, and here COOH. There is one hydrogen. This carbon dioxide is an electrophile which is connected, and an acid group is obtained. This is called, here this is according to the IUPAC nomenclature. Here COOH is given more priority, and here this goes with 1, 2, 3, 4, 5 and 6. So we give IUPAC name as 2-hydroxybenzoic acid, or you can also call it as ortho-hydroxybenzoic acid. This is named as salicylic acid. So this is one of the important questions which is asked. Convert phenol to salicylic acid. So phenol undergoes an electrophilic substitution reaction with a weak electrophile carbon dioxide and results in ortho-hydroxybenzoic acid. Then after Scopes reaction, we move on to another important Raymer reaction called Raymer-Thaman reaction. So here I am going with Raymer-Thaman. Raymer-Thaman reaction. Here, just like how in the above reaction we got salicylic acid, in Raymer-Thaman reaction we will be getting salicylaldehyde. So here again phenol is taken. This phenol is now treated with chloroform CHCl3 and NaOH. So here I am taking aqueous NaOH and CHCl3. This is the reagent which we take in Raymer-Thaman reaction. In above case, carbon dioxide is taken in Scopes reaction, and in Raymer-Thaman reaction, chloroform is taken. Now we will be getting an intermediate compound which is the substituted benzyl chloride. It is not benzyl, it is benzyl chloride. Here you can see, here I am substituting this Na with hydrogen, ONA, and here I am taking CHCl2. This is the part which is connected here, such that certain molecules are eliminated here. Like here you can say minus HCl minus H2O. This is just in order to remember or understand. So here this is the intermediate benzyl, substituted benzyl chloride, that is obtained. Now we'll be taking concentrated NaOH. In the previous case, aqueous NaOH is taken. Now I'm taking NaOH. Now there are two chlorine atoms. These two chlorine atoms are removed and oxygen is introduced into that, such that you are introducing an aldehyde group into the molecule, such that you are obtained with like this ONA and here CHO. There are two chlorines which are removed in the form of NaCl and of course HCl. Now this benzaldehyde, here you can see that Na is given. Now this is acidified again with a mineral acid and removed is sodium, such that you are obtained with hydroxy benzaldehyde. You can see again, just like the above case, aldehyde group is given more preference when compared to the alcohol, and numbering start like this: 1, 2, 3, 4, 5 and 6. So we call this as 2-hydroxy benzaldehyde, or you can also call it as ortho-hydroxy benzaldehyde. And this ortho-hydroxy benzaldehyde is called salicylaldehyde. So these are the two important named reactions, the Cobb's reaction as well as the Riemer-Thamen reaction, which are very, very important. And then the last two reactions, we move on to the next one is a reduction. A reduction in the sense here, you will be taking a reducing agent like zinc. Now I'm taking phenol molecule. This phenol molecule is treated with the zinc. It is heated with zinc. And when heated with zinc, this oxygen is removed. The molecule is undergoing a reduction such that the phenol is converted into benzene and ZNO here. So usually a conversion is asked in examination, like convert phenol to benzene. Then you are using a reducing agent like zinc metal, and zinc is removing oxygen and phenol is converted to benzene. Then the last one is oxidation. Oxidation. What happens when this is oxidized? Like here, we are taking a reagent like chromic acid. So sodium dichromate in sulfuric acid is the reagent. You know about sodium dichromate, Na2Cr2O7 in sulfuric acid, H2SO4. We call that reagent as chromic acid. Now when phenol is treated with like oxidizing agent, here remember this is oxidizing agent. When phenol is treated with oxidizing agent, it undergoes oxidation, and here a di-substituted ketone is obtained. So what is that? Conjugated ketone. Here you can see like there are double bonds here, and here double bond oxygen and double bond oxygen. A conjugated system. So alternate double bonds. The molecule or the system is having alternate double bonds. We call this as a conjugated diketone. Of course here the name is benzoquinone. So this is a ketone, diketone, conjugated diketone. So in this way, these are the important properties of phenol. And initially I was teaching you the electrophilic substitutions, where it includes nitration and bromination. And now here in this on the board you can see Cobb's reaction, Riemer-Thamen reaction, and oxidation, of course a reduction. Cobb's reaction, phenol is converted to salicylic acid, and a Riemer-Thamen reaction like phenol is converted to salicylaldehyde. And then in reduction, phenol is reduced into benzene, and in oxidation, phenol is oxidized to benzoquinone. I hope you all understood here, and I want everyone to go through a flowchart method again. So practice all the properties of phenols and preparations as well as properties. I hope you all enjoyed, and you all be in touch with me. Follow my YouTube channel for the coming sessions. Thank you.